All right. So this module, module 3, is going to be about radical functions. And the thing about radical functions is they technically are polynomials since a square root is the same thing as 2 to the 1/2 power. The reason why they kind of get their own category, though, is in case there's things inside the radical function with that x. This kind of gives it its own little subcategory of polynomials. So we're going to be learning about how these radical functions work. I was going to say how these radical functions function, but that'd be a little redundant. So let's see how the different parts of a radical function. So we're going to learn to interpret the features of this, and we're going to do it through tables and graphs, just like we did with polynomials. All right, so let's take a look here. So if we're looking at this, we have to figure out we have to match these up. So given that the equation is this, write it so we solve for the radius. Well, if we're solving for the radius, we want to divide by pi. So we have area over pi. So we divided both sides by pi. After that, we need to get rid of this squared, which means we have to square root. So we have to do r equals area over pi square rooted. Now, it's important to note that both of them are square rooted. So it has to be this one. The reason why it's r of a, it's saying like r given a. So what is the radius if we already know what a is? A is our input, kind of like when we write f of x. All right, and the next one is given this equation, we're going to solve for the length. So in this case, uh, it's a side length, so that's why they call it S. So in this one, we're going to have to divide by 8. So V over 8, this is equal to S cubed, because it looks like we're dealing with like a cube. And we need to get rid of this cube. So how do we do that? We're going to have to take the cubic root of both sides. So the cubic root's going to get rid of that, and it's going to leave a cubic root here, V over 8. Now, the interesting thing about this, we're not going to get into it now, but you can separate this to do the cubic root of v over the cubic root of 8. And the reason why we would do this for this one and not the pi is because 8 has a cubic root. It's actually 2. But we will get into that later, so I'm just going to move this here for right now. And those are our answers. So this is a nice little warm-up, get the lesson going. I kind of wish there was warm-ups in the middle, so or of each section. That way it's not awkward when I make a two-parter. So always, like I said, watch these videos. I know it's a little difficult because you're watching this video and then to watch another video, but this does talk a lot about the things. It's just kind of awkward for me to just put the computer audio on. So please watch those. Now we're going to learn about modeling these functions. How do these look, in other words? The main thing we're going to learn is that an even root is just like this. An odd root is like this. And the reason why this is think about an x squared. X squared is a parabola. So sideways, it would look like this. The only problem is you can't take the root of a negative number, so none of this is here. Whereas with a cubic function, if we think about cubic functions are like this, and you can take the square root of a negative number. So because of the fact that you can take the square root of a negative number, when you turn it on its side, you do get this bottom part. It doesn't get erased. So that's a cute little fact about these on why This doesn't have any negatives, but this one does. It would have been there except because of imaginary numbers, we don't see them. So why are these important? Well, if you have an area and you know how many spaces in here, you can figure out how many go along a wall. Like let's say you know like 16 boxes go in the squared area. How many would go along the wall? Well, if you take the square root, 4 go along the wall, and it's going to happen 4 different times. So I just realized I should have made that visual. Whoop, whoop, whoop. So 16 of these. Obviously, you can count these, and it's not drawn that well, but you can see 16 fill it up, 4 go along the wall, and it's going to cut up in 4 times. So it's a good way of kind of figuring out limitations in space. We also need square roots to find the side of a triangle. A squared plus b squared equals c squared. And I think I just get, oh, no, that was just part of it. Also, when we're talking about acceleration, so if you ever get into like engineering and things like that, you do need to figure out skid marks because because of the relationship. You're talking about acceleration, that's usually a squared. So when you're talking about deceleration, you're going to involve some square roots at some point in time. So when we're talking about this, the speed's happening, it's going exponentially, but as it starts slowing down, it starts creeping down smaller and smaller. And you can read more into this if you're more curious about the force of skid marks. This does kind of like talk and explain it a little bit of the distance, how fast someone was going based off of how fast they hit their brakes. All right, when we're talking about this, this is the volume of a the volume of a ball. So we would know a volume because we have to fill it up with air. But let's say we wanted to figure out how much space does this take up. It's like, well, how much helium did you put in that ball, or how much air? I guess you wouldn't put helium in a beach ball; it would fly away. But how big is it? Also, when we're talking about volume for x's, let's say we have x by 4. So this side, let's say it's like an inch or something, and the height is this much. Well, we know what the volume is. So somebody dunked this in water and they know how much space it takes up, and they know that the height is 4 times greater than the width, and it is a square. So this and the length and the width are the same. The height is just 4 times bigger, and we know how big the volume is. So they do occur a lot. Um, so also, cubic functions happen a lot when we see something is accelerating and then they start reaching their limit. So for example, think of a car. If you're accelerating really fast, when you go from 0 to moving, you're going really fast. But at some point in time, you reach peak acceleration and you start not necessarily decelerating, but you start accelerating a lot less until it kind of plateaus over here. The engine might still be increasing a little bit, but it becomes less and less observable until the point it actually does reach its limit where it'll stop. Deceleration, same thing as well. When you first hit those brakes, you're decelerating a lot, and then it has less and less effect. This part is significantly less. But I don't think they're talking about hitting their brakes because obviously this would be a lot faster and a lot skinnier because we're trying to stop, unless you're literally going way too fast. All right, and now we're going to be talking about these scenarios. So what type of function are we talking about when we're talking about these given scenarios? So you invest money, this much interest compounded consistently. The model of time needed to depend on this. So this is an exponential function, because what's happening is you have your principal, your initial amount, and it's increasing. So you have your initial amount plus interest. So in this case, interest is very tiny. We have to write as a decimal uh, that many times. Oops. Let me write this somewhere where that doesn't happen. So you have your principal times 1.007, and you're doing this every month. So every month you have to multiply it by 1.7. 1.007. So this is an exponential function because you keep multiplying it by 0.07. Well, how much money do I have? I have my principal times whatever I have, and you're going to keep doing that over and over and over again every month continuously. So that one is not a cube root, or what are our options? Square root or cubic root, because that's an exponential. All right, so we're looking at this next one. A ladder is leaning against the wall. Okay, so if we have a ladder, here's our wall, here's the floor, here's the ladder. The distance dependent on the bottom. So it wants us to know this distance, or blah, 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 blah. Model the length of the ladder. Yeah. So in other words, our c squared. So a squared plus b squared equals c squared, but we're solving for c, not c squared. This is not c squared, it's our c. C squared would be this. We just want c. So when we do that, we're going to do c equals the square root of, well, and that answers our question now, doesn't it? C has to equal the square root of something. So this is a square root function. All right. Model the length of a rectangle in storage prism, square opening, where the depth is 3 times the length of the locker. So in this case, we're doing volume equals 3x times x squared. What's happening is, if we look at it, let me see how well I can draw a 3D shape. Did it a little too long there. What we're saying here is that this is the length, the widths are the same, but our height is 3 times as much. So if we do length times width times height, we get 3x cubed. So that's going to have to be a cube root because we want to solve for x. We get x equals v over 3 cubic root. So we're going to put a little cubic root right there. Model the length of the side of a 6-sided die when we know the surface area. Okay, so surface area is a little more complicated than volume. But the way you do surface area is you're going to do, so the area is the same. We have x and x. But surface area is if we folded out that dice and we had all 6 sides here. All 6 sides. Pretend I know how to draw a perfect square. All 6 sides. And so we're going to have x squared, but we're going to have it 6 different times. So in order to find out the surface area, we're going to have to divide it by 6 and then square root it. So that's why we're going to use a square root. If you guys want to see that, that's just x, x equals the surface area. So surface sub area, I guess I should say area subsurface of 6 square root. All right. And in case you were wondering why I said I should say area subsurface, is usually you're talking about an area. What type of area? And that's why you use your subscript. All right. So model the average cost of producing t-shirts, assuming a fixed cost of that and how much per t-shirt. Well, this is a linear function because what happens is we have our starting cost, our B, and we have our rate of change per item. So a rate of change per item is our slope, our MB. So this is a linear function. Linear functions are neither quadratic nor cubic because there's no exponent to have to cube to solve for the other. The model of a radius of a ball, we already talked about this. It's actually going to be a cube root because volume, the formula for volume of a sphere, so volume sub sphere, we're talking about volume. What type of volume? Sphere. Volume sub sphere is equal to 4 over 3 pi r cubed. All right, so that's a cubic root. Submit those. Oh, I was waiting for it to show my little check marks here, but they're correct, and you can always read up about it here. All right, so differentiate the shape of a graph of a cubic and a function. Compare the graphs. So, in case you guys didn't like my demonstration or you want more proof that I'm just not a crazy person making stuff up, well, I'm not making stuff up at least. Let's take a look at an actual graph. So if you literally type in SQRT, it actually does make a cubic or a square function. I don't know how to type, if it works for cubic root. So cubic root? Nope, doesn't work for that. Oh no. There we go. So you would have to use their little keyboard. I don't think you can see it right now because of my recording tools. Let me make this a little smaller. Nope, apparently my recording tools are stuck here. That is unfortunate. Let me see if I can move these. I cannot move these. Grr. Let me close this and see if I can put them back on. Okay, so the keyboard is actually hidden under here. Maybe you guys could see them, and I just seemed like a crazy person, but I have like little recording tools that let me write on the screen. Okay, so what I'm gonna do here is I need a cubic function. So I'm gonna go to functions, and I'm gonna go to, these are trig functions. I don't want those. I'm not doing statistics. And I don't need to see a distributing, so I'm going to go to miscellaneous functions. Here, I'm going to do this nth root. Our n is going to be the cube, and then we're going to do the x, and then you can see that the green is a cubic function, and the square root is the red function. All right, so if we compare the graphs, the square root only has positive y values, while the cubic root has both positive and negative y values. They both have a curve that where the growth decreases. Not necessarily the growth decreases, but the growth slows over time. So it's growing, but it's just growing less over time. Um, yeah. And then we can say with the cubic decaying less as we go more left for negative x's. That's very specific. So if you guys wanted to cut it off at the growing over time, that makes sense because this is technically growing over time, just negative time. So if you don't want to add this, I'm not even sure how accurate that statement is, so I don't even think I'm going to want to use it. But if you did want to get a little more specific on it, you can try to mess with those words. I don't think I would fault anyone for trying to explain something that complex. But yeah, just grade how you're doing. Remember, if you don't understand something, like if you didn't understand how to explain this, it's like I give myself a 4 because I don't really know how to put words to what I'm saying. I might give, personally, me, myself, I might honestly give myself a 4. So, and if you really did not understand these functions, admit it. Be like, hey, some of these functions don't make sense, or I didn't even understand how I would make these formulas, because some of them are a little strange. Moving on to the next one. So we're going to be interpreting key features of graphs and tables now. All right. So if we look at this, it's important to know what it means by decaying. So radical functions are monotonic. That is, they always strictly are increasing or decreasing. So if you look here, it's always increasing. This one, on this other side, it's always decreasing. You don't see it like, this is another reason why they kind of get their own subcategory. With polynomials, let me see if I can get my tools back on here. Nope, I guess I lost my recording tools. That's fine though. Um, Let me just use my annotate tools. So if we look at this, polynomials go up and down and they grow. Cubics or any type of radical, they either increase or decreasing. You'll find that their average rate of change, so our slope, it decreases over time. They grow less and less and less over time. End behaviors, they're either gonna go all the way to infinity, just very slowly after a while, or they're gonna go all the way to negative infinity. All right, so let's talk about this. So square root function has a very strict domain, meaning that the x values are only positive, and it has a restriction on the range as well, the y value. So the y values are always only positive. Obviously, this can change if we move this function up. So if we move it up, obviously our range is a little different. In this picture, it's y is greater than 2. Or if we move it to the left or to the right, that's why they're very careful in saying that they do have restrictions on it. You might not even have a y-intercept. Like if you move it to the right, you won't have a y-intercept. So you usually have one at 0, but it says you might not have any intercepts at all. And the end behavior, it's either going to end to infinity, or let's say we accidentally make it go upside down by making it a negative square root of x. Then it would go there. So it usually only has one end behavior. And then this is the negative version. So I already mentioned if you flip it over. And then if we put a coefficient in the front, it's going to change the rate of change. So in this case, 1/3 makes it smaller. It's still growing, but just at a slower rate. The negative, anything you do inside the square root is kind of like the opposite of what you would expect it to do. We added one to the x, but we went to the left. So it kind of has this weird opposite effect to it. All right, and cubic functions, on the other hand, when we have a cubic, we do have negatives. So there is no restriction on the domain or the range. They're the same. I'm not a big fan of how they did this, but the idea here is like if you have this negative, if you have this +2, or let's do it with 1. 1's probably better. If you have a +1, this one is a 1, 1, where I marked it. If you have a -1, you're going to have this -1, -1. It's just this idea of that they're the same. So if you have this 3, so it's going to be 3 cubic root of 3. Then over here at 3, you have a -3 cubic root of 3. I think that's what they're trying to say with this. They say it's rotational symmetry, in the sense that it is symmetric, just not this type of symmetric. You kind of have to flip it over, which is essentially just reflecting it over this line. If I folded, oh, not that line, blah. It's folding it over twice, basically. Also, if you make changes to it, so this -4 is on the outside of the square root, so it does go down. The ×2, since it's outside, it does double the growth rate. So, and that's going to affect it. They talk about here how it affects every little point. So if our y-intercept was 0, 0, if we do all of this, it does change it, multiplying the y by 2 and going down. But because this was a 0, 2 times 0 doesn't do anything, but then we subtract the 4, it's still going to make the intercept go down to -4. So it's just saying that the points are affected by the function, but that's just a feature of functions. And right now, since we're already on slide 21, we'll talk about how we can interpret these changes on tables, as well as talking about average rate of change, meaning the slope. So I'll save that for part 2 of this video. I should have it out in the afternoon, if you guys are watching these as soon as they come out. Otherwise, this video is probably out by now. All right, see you guys later.